Alright guys, today is 426, and as I promised, we're going to do an introduction to recursion. Alright, again, I cannot overemphasize how important this idea of recursion is to computers. This is how processes work, this is how random number generators work. It's used in finance and science and all different types of practical applications, but my job is to teach you the nuts and the bolts. Alright. So we're used to equations that are of the form like y equals mx plus b, right? And this is a linear equation, right? And we can plug in an input and we can get an output. Here it's continuous. All right. We're also used to equations like y equals a times b to the power of x. And we know that this is exponential, right? Or geometric, and it's also continuous. Okay, different. We're going to talk about this idea of recursion. Okay, and what recursion does is we can use these to model recursive formulas, right? But these are explicit, recursive, and what recursive formulas do is they usually generate a sequence. So let's talk about what a sequence is. A sequence is essentially an ordered list of numbers, right? Typically we label these as A, right? So you'll have A sub 1, A sub 2, A sub 3, right? And this is our sequence of numbers. It keeps on going, right? Sometimes it starts with 1, sometimes it starts with 0. Typically I'll start with 0, right? And the way it works is there's some sort of pattern to get from one number to the next one, right? Perhaps we're adding a number, right? So to get from A sub 1 to A sub 2, maybe we add B, right? Or let's choose something different. We add C, right? Some constant term, right? Keep adding C, right? And we keep doing that, okay? Or maybe we multiply. Maybe we multiply times C, times C, times C. And this generates for us what is called a sequence, okay? So to do this, we tend to write a formula. There's two parts to it, right? There's an initial value, right? And we call that A sub 0 or A sub 1, right? And this is our initial value, okay? Our 0th term in the sequence, okay? And then we define how to get from one term to the next. So in this case, if we're adding C each time, A sub n will equal A sub n minus 1 plus C, right? And you know what, let's actually change this to a D, right? And we'll say plus D, where D is the difference between terms, okay? And this is how we define it recursively. So this is a recursive formula, okay? You define the first term, and you define how to move from the previous term to the next term, okay? And we can see this is different, right? An explicit formula, you just got one equation, whatever the input is, we get the output. Whereas a recursive formula, you need to know the previous term in order to find the next term, okay? Now with recursive formulas, we end up with two basic types. The first one is arithmetic, right? And arithmetic is this one right here, right? Where you're adding a number each time, okay? There's other ones too, right? I could also have one that's A sub 0 equals a number, right? Whatever that initial input is. And then I can say A sub n equals R times A sub n minus 1. And this one is called geometric. Okay? So here, arithmetic, you're consistently adding something to move from one term to another. Geometric, you're multiplying the previous term to get the next one, right? And then there's other ones too. These are the two most common types, arithmetic and geometric. I can do a combination of both, where I both multiply and add. We use those to build pseudo-random number generators that are linear. But there's lots of different ways that we can apply this. There's some that are completely crazy, right? For example, there's this one here where we've got A sub 0 equals a number, A sub 1 equals a number, and then A sub n is equal to A sub n minus 1 plus A sub n minus 2 whenever n is greater than 1. Right, and so I should have made this come down a little bit further. But here, this is another one. This is a famous sequence. This is actually what's called the Fibonacci sequence, right? I'm definitely spelling that wrong. So Fibonacci sequence. All right. So let's go ahead and take a look at a sequence. And we're going to talk about today how to go from a recursive arithmetic formula to an explicit formula, how to go from a recursive geometric formula to an explicit formula, and vice versa. And we'll also talk about just building sequences given a recursive formula. All right. So let's unpack this Fibonacci sequence, right? Let's actually go ahead here and say that we're going to make this first number 1 and this second number 1. All right. What I can do is I can generate a table of values where I've got n, which is which term in the sequence I'm looking at, and I've got a sub n, which is what that actual term is. All right. So we know here that a sub n, when n is 0, this is equal to 1, because a sub 0 is 1. So a sub 0 is 1. We know that a sub 1 equals 1. So a sub 1 equals 1. Now if I want to get a sub 2, sorry, this should be a 2. What am I doing? When I want to get a sub 2, right, for n greater than 1, I use this, right? So I know that a sub 2 will equal a sub 2 minus 1 plus a sub 2 minus 2. A sub 2 minus 1 is a sub 1. A sub 2 minus 2 is a sub 0. A sub 1 is 1. A sub 0 is 1. 1 plus 1 is 2. So here, a sub 2 is 2. So we can see, to generate any term in the sequence, I simply need to add the previous two terms. So a sub 3 will equal a sub 2 plus a sub 1. So when n equals 3, I'm going to add 2 plus 1, and I get 3. A sub 4, the fourth term in the sequence, all right, technically it's the fifth because we started at 0, will equal a sub 3 plus a sub 2. So here, 4 is 2 plus 3 is 5. A sub 5 will be 3 plus 5 is 8. A sub 6 will be 8 plus 5 is 13. A sub 7, 13 plus 8 is 21, right? And so here I can write this sequence out, right? This sequence, all right, is going to equal, and I just list the terms, 1, 1, 2, 3, 5, 8, 13, 21, and it keeps on going infinitely. But now I can see how I went from what was a recursively defined formula up here to an explicit enumeration of that sequence of terms. Okay? Pretty straightforward, not too bad. Okay? So that's how we can build a sequence. All right, let's go ahead and take a look at another example. We'll just do a basic arithmetic here, right? This time we'll start with a sub 1, right? So our formula is going to be a sub 1 equals 5. A sub n will equal a sub n minus 1 minus 2 when n is greater than 1. Okay? So what am I going to do here? Well, if I want to, I can actually just go ahead and start enumerating this, right? 5, right, is going to be my first term. 5 minus 2 is 3. 3 minus 2 is 1. 1 minus 2 is negative 1. Negative 1 minus 2 is negative 3, right? And I can keep on following that pattern, and I can enumerate the sequence as far as I want. If somebody asks me to list the first 5 terms, I've got them right here. Now, where these come up short is, well, you know, if I want to know a sub 5, it's easy. I just look, 1, 2, 3, 4, 5. It's negative 3. But what happens if I want to know a sub 27? If I want to know a sub 27, what I'm going to have to do here is I'm going to have to figure out what a sub 26 is. And figure out a26, I'm going to need a25. I'm going to need a24. I'm going to need a23. So I actually have to generate this out all the way out 27 terms to figure out what a sub 27 equals, right? So that's a bit of a problem. This is where recursive formulas can have shortcomings, okay? So we want to be able to go from a recursive formula to an explicit formula, right? Now, if we think about this, this is a lot like y equals mx plus b. Whenever you're adding, whenever you have an arithmetic sequence where you're just adding or subtracting a number, you can model it using y equals mx plus b, all right? B will always be whatever a sub 0 is. M will be whatever this constant difference is. So this D is going to go in for M here, right? So here, I'm going to rewrite this formula. I can rewrite this as explicitly as A sub n equals, right, D, which is my constant difference between consecutive terms, times n plus A sub 0. Okay? It's always going to be A sub n equals D times n plus A sub 0. Okay? So here, I gave you the first term was 5. What number would have come before? If there was an A sub 0 here, what number would have come before 5? Well, since I'm subtracting each 2, 5 is what I get when I subtract 2 from 7. So 7 is what would have been there. So this is A sub 0 because this is A sub 1. Okay? My difference is how do I get from one term to the next? I subtract 2, I subtract 2, I subtract 2, right? So if I want to get to 27, I'm going to have to subtract 2 27 times, right? So here, A sub n will equal negative 2 times n plus 7. So now if I want to find A sub 27, I simply plug in 27 for n. Negative 2 times 27 is negative 54. Negative 54 plus 7 is negative 47. So believe me or don't, it's up to you. You can actually go ahead and expand this out 27 terms, but if you were to do this and you were to get all the way out to the 27th term, you would find that negative 47 is it. Okay? Now let's talk about a few things that are going on here. I gave you a recursive formula, and we can see very quickly how we would get this, right? I figured out A sub 0 by going backwards, right? Just adding 2. And then I can write my formula. I also showed you a sequence where this is A sub 1. I figured out what A sub 0 would have been, and I was able to write my formula, okay? So they're pretty much interchangeable. Likewise, you should be able to go from this formula to a recursive formula, all right? So let's go ahead and take a quick look at that. If I had something that was like, hey, y equals, I don't know, let's go with 7x plus 22, and I want to do this as a recursive formula starting with A sub 1, right? Well, here, you can actually generate these, right? If I want to figure out A sub 1, I can just plug 1 in. 7 times 1 is 7. 7 plus 22 is 29. A sub 2, I can plug 2 in. 7 times 2 is 14, plus 22 is 36. Right? A sub 3. And so I can generate this, right? But if I want the formula, right, my formula is going to begin like this. I'm going to start with A sub 1 equals 22 plus 7 is 29. And then here I know, how do I get from one term to the next term? Well, I know that A sub n will equal whatever my previous term is, A sub n minus 1, plus whatever my difference is. And I'm going up by 7 each increment. So plus 7 where n is greater than 1. Okay? So that's how I go explicit to recursive. We already saw how do I go recursive to explicit. Okay? Any questions there? So again, anytime I'm constantly adding or subtracting the same number, I can express that using a linear function y equals mx plus b. All right. Now geometric is going to be a little bit different. Okay. For a geometric sequence, right, I'm going to instead have A sub 1 equals a number. Let's just go with something simple this time. We'll go with 3. And then maybe I'm going to go ahead, I'm going to double that each time, right? So A sub n will equal 2 times A sub n minus 1. Okay? And that'll be for any time that n is greater than 1. Now this one is going to be, we can generate this, right? I know that A sub 1 is going to equal 3, right? A sub 2 will equal 2 times A sub 1, which is 3, so 2 times 3 is 6. A sub 3 is going to equal A sub 2, 6 times 2, which is 12, times 2, which is 24, times 2, which is 48, all right? And it's just going to keep on going, right? So this is a sequence. This one is said to be geometric, right? So this is a geometric sequence. Now, whenever a sequence is geometric, we can model it using an exponential function, right? So we can model it as y equals a times b to the power of x, all right? But here, we're going to go ahead, we're going to plug a few things in here, right? A is my initial value, so this is going to be replaced with A sub 0. B is what I keep multiplying by. Well, what do I keep multiplying by? I keep multiplying by 2. So I'm going to go ahead here. I'm going to plug in R, my ratio between consecutive terms. And then this will become n, this will become A sub n. So here A sub n will equal A sub 0 times R to the power of n. So in this case, A sub n will equal A sub 0. What number would have been before 3? What number would have been before 3 in this pattern, right? So here I keep multiplying by 2, multiply 2, multiply 2, multiply 2. I'm going to do that backwards. Divide by 2, divide by 2. 3 divided by 2 is 3 halves. So A sub n equals 3 halves times my common ratio, which is 2. I keep multiplying by 2 to the power of n. So now I can figure out whatever term I want, right? Let's say I want to figure out, I don't know, what's the, what are we thinking here? The 7th term. A sub 7, 3 halves times 2 to the 7th power, right? So 2 to the 7th power is what, 128? Yeah, 128 divided by 2, 64. 64 times 3 is 192. So I know that the 7th term in this sequence will be 192. All right. And if we were to follow that, we'd kind of see, right? This would be 96. 96 times 2 is 192. And we see that's 1, 2, 3, 4, 5, 6, 7, right? So we know we got it right because that one's not too bad. You can see geometrics grow much, much faster than arithmetics. And again, that's because this is exponential and the other one is linear, right? Likewise, we can do this going the other way, right? Y equals 12 times, I don't know, let's go with 1/2 the power of x, right? I can go ahead here, I can figure out what the first term would be, right? Just plug in 1, right? So 1/2 to the first power is 1/2. 1/2 of 12 is 6. So y sub 1 would equal 6, right? So I can make this explicit. I could start listing terms like 6, 3, 3 halves, and so forth and so on. Or I can go ahead and say here, well, a sub 1 equals 6. And I know to get from one term to the next one, I'm going to multiply by 1/2. So a sub n equals 1/2 of a sub n minus 1 when n is greater than 1. All right. So we talked about how to go recursive to explicit and how to go explicit to recursive. If you're multiplying, use exponential. If you're adding, use linear. Okay? Pretty straightforward. Just show you there's one or two other things we got to be on the lookout for. If they tell you that a sequence is arithmetic, and they tell you that, hey, a sub 3 equals 12, and a sub 5 equals, I don't know, 22, right? We got to be able to figure out what a sub 1 would have been, and we got to be able to figure out what the difference is here, right? So think about it. How many steps does it take to get from the third term to the fifth term? Well, I got to go a3 to a sub 4 to a sub 5. So I'm taking 2 steps. How big is it to go from the third term to the fifth term? Well, 12 to 22 is 10. So how am I going to go 10 in 2 steps? I'm going to add 5 plus 5 plus 5, right? So that's one way I can do it. So now I can start to write, I know that a sub 1 is going to equal a number. I know that a sub n is going to equal a sub n minus 1 plus 5 whenever n is greater than 1. So I'm starting to get my formula. But now I also need to find what my first term would have been, right? So another way to do this is, well, what would a sub 0 be? Well, to go from a sub 0 to a sub 3, I go 1, 2, 3. It's going to be 3 steps. Each step is 5 long, so I'm going to go 15. So if I go backwards, 12 minus 15, this would have been negative 3. So negative 3, right? So you can kind of work your way through figuring out what's going on here, all right? So it gets a little bit trickier if it's geometric. Let's go ahead and take a quick look at that. Geometric. If I tell you that a sequence is geometric, these numbers are not going to work out nice. You're just going to have to bear with me. We're going to say that a sub 4 is equal to 22. I don't know. A sub 7 is equal to, let's go with 15. All right, so this one's shrinking. All right, it happens. So now here it's a multiplicative step, so it's a little bit different, right? We're going to say, well, here I'm going to go 4 to 5 to 6 to 7, right? So it's going to be 3 steps, but these are going to be multiplicative steps. These aren't additive steps, right? And when I do that, I have to go from 22 to 15, right? So here, what I'm going to do here is to find R. It's going to be 15 divided by 22. But I need to do that in 3 multiplicative steps, so I'm going to take the cube root of that number. So the answer here is R is equal to the cube root of 15 20-seconds, right? And now I can kind of go back here, right? So here I can start to write my formula. A sub 1 equals A sub n is equal to the cube root of 15 20-seconds times A sub n minus 1 when n is greater than 1. But I forgot what A sub 1 is, right? So here I'm going to have to go 1, 2, 3 steps, right? 3 steps. So here, this one actually worked out nice because I happen to pick 3 and 3. What this is going to be is it's going to be 22 divided by whatever this is, right? So cube root of 15 20-seconds. And because it's in 3 steps, I'm going to have to cube that. So it's going to be, here these cancel. I end up with 22 over 15 times 22. And so this would equal 22 squared over 15, right? And I can use a calculator to clean these up and get what I want, but this is pretty specific, all right? So again, I can go give you 2 points. You can come up with that recursive formula for me. And if I had to, I also know how to convert that to an explicit formula, all right? There's going to be an assignment on Canvas. You're going to want to go ahead and download it. It's going to have you go between representations. It's going to have you generate various terms of a sequence or series given the recursive formula. And you're going to want to submit that to Canvas. Please email me early and often if you have questions.